there are some very cool patterns in quadratic functions. Okay? The first cool pattern is looking at the differences. So if I click on this, they do a little arrow. A quadratic function, if it has an x squared, will always go over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 7, over 1 up 9. Notice the pattern. Odd numbers. And it's really cool because, like, did you know that? If you added odd numbers up, you always got something squared? 1 is 1. 1 plus 3, the first two odd numbers, is 4. 1 plus 3 plus 5, the first three odd numbers, is 9. 1 plus 3 plus 5 plus 7, the first four odd numbers, is 16. What would happen if I added up the first 10 odd numbers? What would it equal? Right? While you're thinking, I'll write them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What would it equal? Don't add it up. Use the pattern. First odd number is 1. Adding up two odd numbers is 2. Adding up three odd numbers is 9. Adding up four odd numbers is 16. Adding up 10 odd numbers, 100. Because this is 1 squared, this is 2 squared, this is 3 squared, this is 4 squared, this would be 10 squared. This is a pattern for sure. Oh, arithmetic and geometric sequences one? Not this, I mean, yes, because this is also the sum of an arithmetic series where the d value is 2. So that's a whole nother stage of making connections. And we can figure out the formula for that as well, and we find out that it has a square root. Anyways, so this idea, the 1, the 3, the 5, the 7, the odd numbers, is going to be really helpful because sometimes I might give you something like this. I might give you the fact, I might say, here's a parabola. It is x squared plus 4x plus 5. And I will tell you the vertex is at -2, 1. I'm not telling you how I figured that out yet. That's a secret. I'm not letting you ever not have to tell you that. But if I tell you the vertex is at -2, 1, you could draw that. -2, 1. Based on the Desmos stuff that we've done already. Here, I'll put all 5 of them up. In the 5 that we had 3 that opened up and 2 that opened down. The purple and the blue one, they opened down. The red, the green, and the black opened up. Now I just wrote out a new equation. Does this one open up or open down? It opens up. Nice pattern recognition. How many people see the pattern? How many people don't see the pattern? Okay, right hand, you see the pattern, left hand, you don't. It's not, you have to have your hand up. Either way, right? Or if you're doing the test, then you know that. Right? What's the pattern that you saw? The number before the x is positive, that makes it open up. So we're going to find out that if you know the vertex, you could now go over 1, up 1. And so this graph will have negative 1 comma 2 and negative 3 comma 2. Then you could go over 1 up 1, 2, 3. Because it goes over 1 up 1, over 1 up 3. And you would have the point 0 comma 5. Oh, plugging in 0 would be easy to figure that one out. But you would also have negative 4 comma 5. And if I wanted to find the next point, I could go over 1 and up 5. So this pattern, the 1, 3, 5, is going to be really helpful because once you found your vertex, you now can find a whole bunch of points fast. Faster than plugging them in, right? I think it's a lot faster to go over 1, up 1, than it is to plug in 1 and do all the mental math and go and figure out, or sorry, plug in negative 1. Negative 1 squared is 1, minus 4, plus 2, right? It's faster to just go over 1, up 1 to find that next point. So this pattern is really powerful, okay? And we're going to find out if there's a 2 in front, then everything gets doubled. So instead of over 1 up 1, over 1 up 3, over 1 up 5, it's over 1 up 2, over 1 up 6, over 1 up 10. They would get doubled. And if you had 3x squared, it's going to get tripled. So we're going to notice that pattern a little bit later. But for right now, we'll get to example number 2. And in example number 2, we have to try to figure out, does the pattern have this over 1, up 1, over 1, up 3 kind of pattern, or doesn't it? Does it have symmetry, or doesn't it? So, is this a quadratic function? Sometimes a table isn't the easiest place to see, okay? So what you could do is you could look at the graph. You would have 0, comma 2, 1, comma, negative 1.5, 2, comma, negative 5, 3, comma, negative 8.5, and 4, comma, negative 12. Does that look like a U-shaped graph? Or does it look a little more like a straight line? And if we look at what's happening as we switch, we're going down 3.5, down 3.5, down 3.5, down 3.5. This is a line. And if the difference that you're always switching that's your slope. So the first one is a line with a slope. What about the second one? We're going up 8.5. Oh, this is great. They did another one where you're always going up the same amount. If you're always going up the same amount, this one too is going to be a line with a slope of 8.5. On the example that the textbook has, if you want to see one that actually makes it quadratic, we would have to go here back to the ones in the textbook. Down 5. down 7, down 9, down 11. If you get a pattern where the first differences are increasing by a certain amount each time, and then the second time you check the differences, it's always the same, that will make it a quadratic graph. But here, we're actually doing some first-year calculus, which is kind of crazy. When you look at when do things turn constant, if it takes, see how it's always -2 after the second time? If it takes 2 times to do that, you've got an x squared. If it does it right away, you've got an x graph. If it would take 3 times to do that, you'd have an x cubed graph. And so on, and so on. X cubed graph goes like that. Okay, so, question number 6 for this one. And I will let you work on those questions now for the rest of the class. We'll leave example 3 for Monday, maybe? Because we have a quiz tomorrow. Okay, tomorrow, after our quiz, I'll give you time to work on a review.